Right, everyone. So, yeah, I'm Rory Evans. I'm a first year PhD student, and this is some work that I've started over the last 9 months, and I'm going to be carrying on through the rest of my PhD. I'm at Oxford, where I'm working in the Space Instrumentation Group in the Physics Department, with Simon Calcutt and Neil Bowles, who are my supervisors. So, basically, in Oxford, we have a history of doing a lot of much larger instrumentation on planetary and Earth-observing satellites, and now we are considering putting that into a CubeSat type package to try and see what new science we can approach in a different method. So to explain some of that background, I've got some of the missions that we've worked on most recently, and these are all infrared missions. We do a lot of infrared science. There are other things that we've worked on, like the Mars Insight seismometers, but the infrared science is what I'm interested in. So we work with the Cassini, the Compact Modular and the Compact Sounder. A lot of the work is done with people like JPL as well, in collaboration, and we do a lot of work with Reading too on the filters for those kind of systems. The ones which are most relevant for talking about today are the Lunar Reconnaissance Orbiter, where we worked on the Diviner instrument, and also that instrument's derived obviously from the Mars Modular Sounder on the Microbolometer. And those are filter radiometer instruments, which is basically what the instrument I'm presenting is today. The work is derived from the most recent instrument we have, which is the Compact Modular Sounder. So this thing launched on TechDynamosat in 2014. This was a UK technology demonstrator. And basically we put together this instrument package for this satellite in a very short time frame on a very limited budget, and kind of doing that mission is, I think, what led us towards the CubeSat type idea, because we sort of demonstrated a lot of the techniques that you use when developing a CubeSat instrument for that small, low power, low cost, and fast development package on the TechDynamosat instrument. And we did a lot of work with that with RAL Space in Oxford as well. So what kind of science do we get from the thermal infrared instruments that we work with? So as an example, going back to the Diviner lunar radiometer experiment. So this is a 2 telescope infrared radiometer, and basically what it has is an infrared detector and a series of filters placed in front of parts of that detector array. And then as the satellite looks at the moon, it's able to map different channels on the surface in the infrared wavelength regions. And there are kind of two main types of measurement that we look for with this. So there's the mineralogy type measurements, where you look at 3 very focused bands. So those are shown on the left-hand diagram, and these are centered at around 8 microns. And these are an indication of silica mineralogy on the moon. And basically, by looking at these 3 bands, we can pick out the peak feature, the Christensen feature, and that tells us about those silica minerals. To actually do that, though, you also need to measure the temperature of the surface so that you can calibrate out the actual surface temperature to get the emitted fraction of light. And to do that, we need to measure in longer wavelengths, and that's where we measure across 10 up to 400 microns with the longer wave infrared. So that gives us the surface temperature. They can measure down to, I think, 40 Kelvin with the series of filters that they have on that, but obviously the signal gets very low, so it's difficult to use that data. In terms of what they produce as science maps and the work that we do, so on the left there's one of these mineralogy maps, so it shows the variation across the surface, and you see all sorts of interesting geological features picked out from this data. Just looks at, from my background as a physicist, is a lot easier for me to understand, not being a geologist, is the sort of physical properties, so things like thermal inertia and rocket movements, which you can get from the temperature measurements. So by building up a map of temperature by local time on the surface, you can look at things like the change through the day of temperature, and the rock concentration in this case, for like boulders and so on, is looking at the thermal inertia and seeing how that changes. And this is useful for if you want to do future landing missions, landing sites, based on how rocky that terrain is going to be, or how porous or kind of the topography of the actual terrain can be seen in this data. So beyond the moon, we also have an interest in things like asteroids. So my supervisor was the lead on the Castaway mission that was presented yesterday by Calcutt. And so we would have some interest now in following up with asteroids. And the infrared imager that's sort of put onto that proposal is effectively what I'm now trying to condense into a CubeSat package. In terms of asteroid measurements, we do a lot of the same things that we do on the moon. You look at the spectra of different types of minerals on the surface, and then we look for features, and then you choose specific bands in the infrared to pick out those features by proportional emissivity in this case. But to achieve this, you need to get very precise measurements of the spectral bands. On the order of 1 to 3% to actually get between different mineral compositions. It's a lot more difficult when you have things like space weathering and hydroponic systems and so on. And then going back to the physical measurements as well as the compositional measurements, we can also start to add a lot more knowledge to the understanding of the thermal effects on small bodies as a result. We were able to map these bodies fully out of the method. In particular, the Yarkovsky and York effect is something we'd like to look at, the spin off and the change in orbit for an asteroid based on the heating and rotation of that asteroid itself. And by getting high resolution, high radiometric accuracy temperature maps, we'll be able to add a lot of knowledge to understand this. So, as I said, we developed this from CMS, the Compact Modular Sounder, in 2014. And this thing is an Earth-observing infrared sounder. So basically, it's got an onboard Blackbody calibration, which helps us to achieve some very precise measurements, and that's sort of kind of the core of what we want to achieve with these instruments, the high quality of calibration. So the Blackbody is key. We have this cavity Blackbody, and then we very carefully control the temperature of that Blackbody. So we heat it up and then we let it drip. And by precisely knowing that temperature, we can precisely know the radiometric filters within our instrument, and we can measure the radiation of any part of the instrument by using a full calibration system. So that's based on the pointing mirror, which we have. So looking at different targets and looking at the Blackbody will deal with that. As I said, this demonstrated a lot of the important features that we want to see in something like CubeSat. We did this on a very short timescale, it was very cheap, and it's also quite small, so it's a small volume. It's definitely not a CubeSat volume. That's something that we need to heavily improve in the future. We also have a couple of other things, so the detector resolution is pretty low, so if you want to do mapping, it's not ideal, it's very limited. And there's a few other things, such as the mirror driving rough, for example. So that leads us into our CubeSat-like concept. And this is a 6U CubeSat. And the initial design I've shown here is designed for Earth observation in the first instance. So we have looked at applying this CubeSat to atmospheric retrievals from either LIM or Nadir sounding cases. And we had a study in 2015, a mission design report by the Center for Earth Observation and Instrumentation Group, Space Technology Group, which is a horrible acronym, but yeah. And we typically fit this into a 6U instrument. About 4 of that is the payload itself, and then we have about 2 units of avionics and communications, batteries, and data handling units. So there's a couple of key features in this which come across from CMS. So as I said, we have a pointing mirror, which is at the front, the scan mirror, and that can rotate to 2 different targets. That also can rotate to that calibration target, which again is key for giving us the high radiometric precision that we want. We then have an input telescope, and the input telescope has an initial focal plane. And one of the things that we do different is by using an intermediate focal plane after the first telescope, we put our filters there rather than placing them onto the detector itself. This means that we can reduce thermal impact of the detectors, thermal impact of the filters, which will absorb and can be very difficult to control. We also get a geometric reduction between the two elements. So the initial telescope is, has an F number of 3.4, whereas the final detector array from the transfer optics has an F number of 1.7. So that gives us a geometric reduction in the size of the focal plane. So we can make our filters quite as large, make it a lot easier to integrate onto satellites. It also means we get less impact from that more difficult to control thermal environment of the filters themselves. And that's kind of key to our satellite design. So this is going back over that. So we have a 1.7 F number final focal plane. Currently we're looking at around 640 by 480 or a 1024 by 768 pixel array to do our imaging. I think the next slide and detectors will talk about that in a minute. But filter-wise, we, as I said, film work is ready quite well. And they will probably provide filters for this. We haven't actually decided any filters as of yet because we haven't really got a target for this mission. So they can be chosen for various different things. And looking back at the MCS and the Diviner instruments, it's quite easy to take a filter radiometer and swap out the filters for a different target. So we're not too concerned, I think, about focusing immediately on the target itself. We know that things like Blackbody will have broadly similar filters, and they should be achieved fairly easily. We're looking at as large as we can get, about 60mm aperture. It's a little bit difficult to do anything else. And I won't talk about the focal plane. In terms of enabling technologies, the detector array is something that's really allowed us to miniaturize this instrument now and not before. So we can now get these high performance infrared microbolometer arrays. Basically, we've measured the temperature change of a small silicon pixel as it heats up. And this gives a good quality response from 7 to 15 microns, and we think we might be able to get about 20 microns if we have a different detector package on there. With the optics we've got about 118 microradian field of view for a single pixel. This gives us good quality imaging for something like an asteroid. We use this kind of instrument as a baseline for half of the program that we're working on. But that gave us ample performance for something like that. So it easily applied to a target like an asteroid, for example. We believe we can get packet cooling down to, I think the minus 40 I've got here is a bit optimistic, at least minus 20 degrees, heading towards minus 40 to get the best performance on that detector array. Well done. And it's low power as well, which is the reason for CubeSat. Back to calibration, so we have it's on board Blackbody. This is based on the CMS one, so we've got some heritage there. And it's just a simple V-group Blackbody, but we think we can get less than half Kelvin accuracy, which is enough for atmospheric retrievals and easily enough for the kind of surface measurements that we can do on asteroids. Going forwards, we've got a grant to start to look at to actually build some instrumentation to test the performance and also to test the pointing performance, which is critical for atmospheric retrievals, less critical for surface retrieval. And so in the future we're going to build a test bench using spare flat optics of the derivative instrument CMS, and that will allow us to understand how this satellite performs and then in the future move towards actually finding in order to build a real version of this satellite. So I think with that I just want to thank the members of the consortium that developed this mission. So we have this design report, and that used the Centre for Earth Observation Instrumentation Space Technology Group, and also the University of Oxford, RALSpace, the Space Applications Capital, and Firespace. So thank you very much. Thank you for questions.
Thanks very much, Rory, and we'll take some questions. Thanks for your talk. I've got two questions. The first one is probably I missed it. How many filters can you pack in your CubeSat?
So we think we can get at least 10. So there you go. So this plot, this is from our part of our aim proposal, and we think we could have a central broadband imager, and then we put those towards the side of the detector, and then we can use both the large imager just in the broad infrared band. Then we can also use push-through mapping using those filters on the side of the array. We can use both, and around 10 filters.
And the second quick question, can you do something to reduce the 4 kilo mass?
Yeah, so currently we're looking at optimizing both the mass and the volume of the whole system. 4 kilograms was the CMAS one, I think. I don't think we have a baseline for our CF instrument mass, but we are looking at this 4 kilo volume, but again, I think we can also get that down. So we're looking at now a shorter version of the Blackbody calibration target, so that might be able to crack down into 1 unit. I think we can get it down to about 3 units. So, and I can't really say what the math is going to be. We haven't built it yet. So.
We should do.
Yes, we should.
So it's really good to see, I think, instrument and scientific groups like yourselves trying to miniaturize past instrument heritage from planetary missions into a CubeSat form factor. So just to say that's really good work to see. Have you thought for the asteroid observations which targets you would like to visit to operate the instrument at? Has there been some work there on the science side?
No, not at all. Apart from the work that was done with Castaway included CubeSat options, and also the thermal emitter is based on this system, based on CMS. So anything that we looked at for that would be suitable for this instrument. But the main issue with going out to asteroids is that this, in its current incarnation, is based on Earth observation. So there's a load of stuff that we need, like thrusters and better attitude control, and also deep space performance to actually operate that far out. So the design would change quite significantly. So I don't quite early, I think, to the target for now, until we know that it will more generally be in space.
I think when you do get to that point, we'd like to know for sure what the preferences would be from a scientific point of view. Whether you would like an S-type, C-type, or whichever type of asteroid X-type. So,
yeah.
Good to understand.
I suppose it also depends who gives us money for it.
We can talk about that as well.
So I didn't quite understand the significance of the scan mirror. I do for the calibration term, but is it a whisk-broom instrument or a push-broom?
Push-broom. So we would operate with the mirror fixed while we do push-broom imaging. But that also just allows us more flexibility for choosing targets often without slowing spacecraft. And yeah, the calibration target is the main reason that mirror do exist. So we can get the full track calibration. Otherwise, we would just miss that mirror if we had like a slicing target or something. Any further questions? In that case, let's thank our speaker again.